Greetings indeed. Alrighty. So, let's see. How is everyone's ability to see me and hear me today? You're welcome, Rob. Hopefully so good. So far so good. Okay, cool. Let me just start you guys with a practice problem. Cool. Let's not start with red. So we remember this happy formula, yes? Let's go ahead and say that I have oxygen gas, 12.5 liter tank, and 25 degrees Celsius. Yes, fixing the cable definitely seems to have worked, so cool. Okay, find me the missing number. Anybody can tell right away what's the missing value here? Indeed, we are looking for the pressure. Before we go ahead and plug everything in, do we need to do anything to any of these numbers? Indeed, we must get rid of that pesky Celsius and turn it into a happy Kelvin. So doing that, you should get 298.15, with the 1 being the significant digit there. Well, we're going to force it, Rob, just in case. Alrighty. So, we can see that pressure will be nRT over V. It doesn't have a choice, exactly. Welcome to chemistry. Oh goodness, I have no room whatsoever. Okay, you know what? Forget it. I'll just write it on a new line. Blah. Okay. We have 0.08206 liter atmosphere Kelvin mole, 298.15 Kelvin over 12.5 liters. What about the volume, Zoe? Okay, cool. Moles will cancel with moles, kelvins cancels with kelvins, liters with liters. Yeah, if you guys... I think she was actually talking about the tank volume, being the gas volume. I know. Unfortunately, volume for loudness and volume for amount of space. So, cool. Okay, someone calculate this for me, please. Someone trustworthy. Who is it that we don't trust again? Don't remember. Manuel, I thought he was okay with calculations. We just can't trust his, spelling. I don't remember. Oh, Samville. Okay, that's right. Oh, but he got the same thing, so that's good. Okay, yeah, I would agree. It looks like we have 3 sig figs here. So we have 6.38 is our number, and we should have atmospheres as our units. Okay, any questions on this? Easy formula, yes? You just plug in your stuff and away you go. This chapter should not be too difficult for any of you guys, so I hope. Is it just lagging you out? Okay. Any questions on that stuff or with anything else with this equation? See, that's because I'm using nitro, Rob. I paid for you guys, so it's worth it. Indeed. Alrighty. I have a fun fact for you guys. What if I were to tell you that R equals R? Would you believe me? Yeah, you never would, but it's true. Believe me. R is the same thing as R. Right. So, if we take our equation here, we can go ahead and solve this for R. We can see that R equals PV over NT, right? And since we know that this could be for any PV, N, or T for any gas, we can say that for any other gas, the same thing is also true, right? And since R is equal to R, we can say PV over NT equals PV over NT, right? And just like before, we can throw ones on all of these and twos on all of those. So for any, gas that we're messing with, indeed, we can mess with these things and figure out what's going to happen. It's just, the same type of equation as before. So typically this will be used for, if you are changing one of these conditions. So if you're changing the temperature and you want to see what's going to happen with the pressure, if you keep the volume the same or something, or if you want to change the volume and pressure at the same time and see what happens with the temperature. So you can mess with a whole bunch of different variables now and predict what's going to happen with the other one. Now, typically, you're not messing with the number of moles. That's just typically harder to do. So very often we don't even worry about that with this formula. We just say PV over T equals PV over T. This is called the combined gas law. And we use it for when PV or T are changing. Okay, so that's this guy right here. PV over T equals PV over T. Very nice, right? An example of something you would use this on is, let's say, a gas in a 5-liter vessel has a pressure of 1236 torr at, I don't know, how about 142 Kelvin. Okay. What would the pressure be if, let's say, the gas is moved to a 10-liter vessel at 500 Kelvin? So, we can see here that we have a volume, a pressure, and a temperature to start with. And we also have two variables for what we are ending up with. And we also know that the question is asking for pressure. And silly me, I have not indicated a unit. Let's go ahead and say I want the unit in torr, just to make things easy for you guys. So we are looking for the pressure. In this case, we typically just call this P2. Let's go ahead and assign some variables to these numbers. So our equation is P1V1 over T1 equals P2V2 over T2. What should the 5-liter number be? What's that going to be? Yeah, that'll be V1, right? And how about 1236 torr? P1, yep. And 142 Kelvin? Exactly. So we have our left side of the equation already done. What are these other two numbers going to be? V2 and not quite P2. T2, exactly. Yeah, that's the temperature. All right, so we are missing P2. That's the one we're going to solve for. So, since we know, I'm just going to write it again. P1, P2V2 over T2. What we can do is we can solve this equation for P2 and then plug in our numbers, of course. Okay, let me move this guy out of the way for you. See if we can get all of these. Sorry, Zoe, just unfortunately, just slightly off here. Okay. So we can just go ahead and either just plug in our numbers, or we can solve the equation first and then plug in. I typically just like to solve the equations first, but you are always welcome to do it however you like. All right, Zoe, let me know when I can move back down once you're ready. Okay, here we go then. So we are looking for P2. So we can isolate that variable. This is just algebra. I'm not doing anything crazy here. So right, I've moved this guy up to the top of the other one. I know. And I've moved this guy down to the bottom, right? That just made everything a whole lot messier, I know, but if you don't want to do the algebra first, that's fine. Just go ahead, plug in your numbers, and solve it after. That's going to work. So, if we go ahead and do all this stuff, I don't remember any of our numbers. Okay, let's see. 1236 torr. The volume was 5, and the temperature was 500 for T2. And then temperature 1 was 142 Kelvin. And then volume 2 was 10 liters. Okay, again, simple algebra. So looking at our units, liters and liters, kelvins and kelvins, those should all cancel out. And we should be left with torr. Open my calculator, if you would not mind. Why can't I change it? Oh, because it's over there. Okay, duh. You can do it, guys. Calculate for me. Okay, that seems reasonable. And I like that Marissa has already applied her sig figs. That's awesome. Okay, so you guys look like you're calculating correctly. That's awesome. But we will round it to 3 sig figs. Because 5 liters and 500 kelvins and 142 are all 3 sig figs. The other 2 numbers are 4. So we're going to want to do 3 sig figs. Alrighty. Questions on that one? Yeah, okay, cool. So thankfully this stuff should just be like math. That's all it is. There's not too much chemistry here. Okay, cool. There's one last equation that we have here. All of the stuff that we've done so far, it's been kind of if we're dealing with one gas. But we can often have mixtures of gases as well. So let's see how we're going to work with that. Alrighty. What would the pressure be if I have 1 mole of gas at, let's say, 273 Kelvin in, I don't know, a 22.4 liter vessel? Calculate for me. Atmospheres would be a good unit for this. Let's see if Shelby has the number. Indeed, it's 1. Haha. I like that I tricked you guys. Well, not really, but it's kind of cool. Yeah. 1 atmosphere, right. Does this pressure change if that gas is oxygen versus nitrogen versus chlorine or helium? No, it doesn't, right? Because nowhere in our equation does it matter. Do we have any part of it that talks about the identity of the gas? All we care about is the temperature, the volume, and the number of particles. That's the moles. So it does not matter what the identity of our gas is. All right, so let's look at this, and let's say that this is actually a sample of air instead. We have 1 mole of air. Alrighty, and air is, if we have 1 mole of air, that's about 0.78 moles of nitrogen, and about 0.21 moles of oxygen, and 0.01 moles of argon. That's pretty much what air is. Of course, you don't need to memorize these. But we can actually calculate what the amount of pressure each one of these guys would have. So let's go ahead and do that. If we had 0.78 moles of nitrogen, what would the pressure be for that? So instead of using that 1 moles, you're just going to use 0.78 moles, but you're going to use the same temperature and volume as before. It is indeed the same. And guess what? The pressure of oxygen will be 0.21 atmospheres, and the pressure of argon will be 0.01 atmospheres, if you were to calculate all of these. So we can see here that all of these, if we add them up, let's see, Elsa's writing something, let's see. How do we calculate it again? P is equal to nRT over V. So you're going to use the 0.78 moles for N. R is 0.08206. The temperature is 273, and the volume is 22.4. So you're going to use those numbers to calculate these. Okay, so cool. If you see, we add these all up, we should get 1 atmosphere, because these also add up to 1 mole. Okay, so what we can see here is that whatever the percent, let me just actually define something for you guys. These guys here, this one, and this one, are what are called partial pressures. Okay, and that's just the pressure of one gas in a mixture of gases. And for those of you who are more visually inclined, here's our container. And let's say these blue ones are our nitrogens. These guys are our oxygens. And how about purple? Since there's not very much of that, we'll just leave it as 1 purple dot. That's our argon. All right, so this is what that kind of is looking like. So you remember that as the gas molecules are moving around, they bump into the walls, right? In this case, we could have a blue wall bump into the wall. We could have an orange one bump into the wall, or that purple one can bump into the wall. So it just depends on which one it's going to be. So since that purple ball is all by itself, you know, there's not very much of the purple in there, the purple is going to only give a small amount of pressure to the overall system. But we can see that there are a lot of blue ones that are all going to be hitting the walls fairly frequently. So a lot of the pressure will be generated from the blue ones. And then the orange ones are kind of in between there. Okay, so but all of them overall will contribute to the overall pressure. But if we wanted, we could figure out the pressure of just one of those. Okay, does that kind of make sense? I'll give you kind of a formula for how to do this as well. But I just wanted to see if this kind of little picture analogy makes sense to you guys. Okay, so in that case, here is our equation. And in this case, let me just say, let's say it's gas X. So that's going to be the total pressure times the percentage of that particular gas in your mixture. So if we saw here, nitrogen was 78%, right? Which is 0.78. And so, since the total pressure was 1, all we had to do was multiply 0.78 times 1 to get the partial pressure of nitrogen. And we could do the same with the other ones. Okay, so all we have to do, if we want to find the partial pressure of the gas, let me go ahead and label these for you guys. Partial pressure of gas X, and that is the decimal percent of X in the mixture. Put a little bracket there. Okay, so it's the percentage, but in decimal form. So instead of 78%, we used 0.78 for that one. Alrighty. Let's go ahead and see this in an example, and I think that'll help to make it a bit clearer for you guys. So, let's say we have a mixture of 95% oxygen and 5% helium. Okay. And let's say we have 17 degrees Celsius and, I don't know, 12.5 liters. And the total pressure is 215 atmospheres. A lot of gas in there. Let's see if you guys can tell me how many moles of oxygen I have and how many moles of helium I have. All right, so from this problem, what variables do we see already that we can use potentially for a gas type equation? Any ideas? Any ideas? No. So we do have temp, volume, and pressure. So we could find the moles, right? We can figure out, using these three, we could find the total moles of the entire gas, and then use our 95% and 5%. Or we can go ahead and multiply those percents by the pressure, and then solve for each gas individually. We could do it either way. So let's go ahead and let's do it the first way. Let's see if we can find the total moles of gas for this thing. Can we use these numbers directly? Yeah, we'll do both ways. Is there any problem with any of these numbers? Yep, always that's C to K, so that's going to be equal to 290.15 Kelvin, if I'm not mistaken. Someone go ahead and check that. But we remember magic equation is here. So if we're finding moles, that means moles is PV over RT, which I realize again I need to be writing further to the left so that I have room. So the pressure, what's that going to be? I guess I've already written P equals 215, so I'll write that in. What's the volume? And then we're going to divide by our favorite R. And our last number, of course, was the 290.15 Kelvin. All right, so we're going to go ahead and see what units cancel out. We should be left with moles, which is good. That's what we're looking for. Let's see. All right, I'll do this for you guys. Computer, what's 215 times 12.5 divided by 0.08206 divided by 290.15?
The answer is 112.874. Did that answer your question?
Yes. Okay, cool.
Thanks for your feedback.
Yes, go away. Okay, cool. So, Alexa has solved the equation for us because none of you want to calculate stuff anymore. Oh dear. Look who's here, everyone. We have our visitor. Come here, little one. Nope, he's just standing in the doorway. Okay. Are we done with this, by the way? Not quite. Indeed, we are going to want to use our 3 sig figs, right? But we actually have stuff to do. We have this 95 and 5% stuff here. So we know that this is the total number of moles. Okay, because we use the total pressure. Right? So, if we remember that we had 95% oxygen, 5%, oops, oh my goodness. Let's just start that over. We can figure out, of these moles, what portion of that is oxygen and what portion of that is helium. Sorry guys, Gumbo came in, but then he decided not to hang around any longer, so sorry. So what we can do is take that, by the way, we know it's 3 sig figs, 112.874. We can multiply this by 0.95. That's 95%. Perfect. Okay, great. So Shelby has done the work for us. So she got 107, let's say, with 3 sig figs. And then the other one was, this was oxygen, and then 112.874 moles times 0.05, and that was helium, which she says is 5.64 moles of helium. Awesome! So there we go. That's our answer. We have in this tank this many moles of oxygen and this many moles of helium. All right, so does that kind of make sense? So what we did was we did the total moles of everything in the gas tank, and then we just multiplied that by our percentage to get the moles of each one. What we could have done also is use that relationship before of the partial pressure idea. Oh my goodness, this formula up here. We could have used that first. So if we see that we had 215 atmospheres to begin with, we could have multiplied that by 0.95 to begin with. Computer, 215 times 0.95.
215 times 0.95 is 204.25.
We could have found the pressure of oxygen first, and the pressure of helium. Looking at this, that's going to be 11.75 atmospheres of helium. And then we would just plug those guys into the ideal gas law. So for oxygen, we would do the pressure of oxygen. Moles of oxygen would be pressure of oxygen times the volume over R and T. I'm sorry, I lied to you guys. I don't know how to subtract. Thank you. Okay, which would be 204.25 atmospheres times the volume, which was what, 12.5, I think? And then R, 08206, and then the 290.15. And doing all this, you should get about 204.20. I'm not sorry, not that. Whatever it was last time. What did Shelby said? 107. Okay. Okay, so you could do it either way. You can do it for each gas separately, or you can do it for all the gases together and then separate them at the end. Okay, so either way, this would work out. Okay, so basically all you have to do is just like kind of do it twice if you have 2 gases. And if you had 3 gases, you would do it 3 times. But that's all it is. There's nothing too crazy here. Indeed, so it's just more work. But it should not be too difficult conceptually, I hope. I know, we all like the least amount of work. I personally think it's easier to do this way, the first way that we did it, because we only have to do the ideal gas law once, and then we just do our percentages at the end. But if you wanted to do the gas law twice, you totally could. You could then do the moles of helium would be the pressure of helium times the volume times over RT. And blah, 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 you would get the same answer for helium that we got before. Okay, but again, you can use whichever way you like. All right, let's see what Zoe's got to say. The second table. Okay, good, because I was going to say I have no idea what you're talking about, so... if you could show me the lab, I guess I could maybe help to answer that, but I have no idea what he's shown you guys, so yeah. But from what it seems, from what I've read, from what other people were saying, that it does look like you have one set of data, so you would only have one table. Do you guys all know what you're doing for that lab, by the way? Kind of? Okay. Yeah, because in the real lab you would do the experiment twice, because it's a pretty fast experiment, and then you would just make sure that your data agrees with, agree with each other. Okay, I'll give you a little hint for the lab here. Anytime you're looking for molar mass of something unknown, I'm sorry, Zoe. Yeah, I guess so. That's always going to be your mass over your moles when you're doing it experimentally, which you'll find is the units of grams per mole. Yay! So whatever moles you calculate from N equals PV over RT, and then the mass that you've got from weighing it, that's how you're going to put those guys together, okay? So make the units happy. Okay, let's go ahead and I want you guys to try one more of these problems, because that's really it for gases. Again, nothing too crazy here. It's just when you have multiple gases, you just got to do a few more steps. So, let us see. Someone give me a gas. What's your favorite gas? Krypton. Okay, great. And driving? Or you're driving? Okay, well, you can look at it later, Zoe. Okay, so Krypton, let's say we had 70 gas for driving. I like that. Okay, and then 28% of oxygen. Okay. That gas would be heptanes and octanes, but separate. We'll use easier things here. Okay. Or ethanol. Ethanol could be a gas too. So, let's say we've got these two in this proportion. And let's say I have a volume of... What's someone's favorite volume? Throw out a number for me. Loud? 420, huh? Okay. Of course. Shall we just say 69 atmospheres while we're at it, too? Okay, and then temperature. Give me a temperature. 333, okay. Celsius or Kelvin? Okay. Make it easy for yourself. Okay, that's great. Alrighty. I want the grams of krypton and the grams of oxygen. Okay, hint. Find moles, then use molar mass. Okay? Have fun! I'll give you guys a few minutes to do this, and then I will work through it with you. Okay? So you're welcome to use, whatever method you like. The only thing here, we have one more step, is that once we find our moles, we're going to convert them to grams. Okay? And hopefully you remember how to do that. By the way, don't forget you guys have homework that is due tonight, so don't forget to submit that, okay? Let's go on Canvas and see if I am ready to give you guys more homework. You guys want more homework, right? Let's see. Would that be homework 7? Yes, you could very easily do this. Okay. So homework 6 sample is actually for chapter 6 stuff, but since we skipped chapter 6 for now, we're going to skip that homework for now. So I will make homework 7 due for you guys, and you'll submit a picture or PDF. That'll be due in a week. Cool. Though I want this to be a little easier for you guys. Okay, so for homework, technically, homework 6, like, since all these homeworks are already up there, homework 7 is the one that is on this content. Homework 6 will be for stuff that we'll cover later. Okay? So we're just going to do these out of order also. So don't worry. Okay, so I'm going to make this easier for you guys. On the last question, just give me the grams of oxygen. Don't worry about minutes. Okay, so that is in writing, so you guys can cite this later. But don't worry, for homework number 7, don't worry about the last question. It's going to ask you how long it's going to last. Don't worry about that. Just give me the grams of oxygen, okay? So you'll see that when you get to the homework. There's only like 5 questions or something, so it's not too bad. Oh, shame on me. Krypton has an R. Alright, let's see what Arpan has got for us. Perhaps it is the answer. Okay, that seems pretty reasonable, I hope. I mean, we do have quite a big volume here, so, I mean, it could totally be like that. Okay, are we ready to work on this, or do you guys want a few more minutes to work on it yourselves? Okay. We can do that, Cassidy. Is that for the lab you're asking, Cassidy? Oh, so for this, oh, I'm sorry, I realized that could be confusing. This stuff up here, this is for your lab, so don't worry about this part here. This stuff is lab, right over here. Okay, so don't even worry about that. Once you find your moles of krypton and your moles of oxygen, whatever those are, you're just going to use the periodic table to figure out their molar masses and then multiply by that. Okay, but you'll see it in the example. Okay? So, let's do krypton first, or let's do oxygen first. Why not? Because Arpin has given us a number for that. Okay, so let's do it the first way, if that's okay with everyone. We're going to find the total moles, and then we're going to multiply it by 28%. All right, so N equals 69 atmospheres times 420 liters over our favorite number, and then 333 Kelvin. Arpin, did you happen to have the number for this one? Or anyone else? 12 moles? Can I have a few more decimals? Oh dear. So Samville is known for lying to us, but let's just find out real quick. I'll do it myself. Again, both I agree with Marissa and Elsa here. I got 1060. I don't know how you would get 12 because it's 1060.529. Yeah. So I do not know how you got 12. So just double check your calculator. This is what you should get. So, and then we do want 2 sig figs on it, but let's keep the number for now. Okay, so this is why you guys always gotta practice your calculation skills, okay? So, because it's all well and good if you understand the concepts, but if you can't calculate it and it's multiple choice, not much I can do for you there. So, unfortunately. So, alrighty. So, now that we have that, we know that this thing was 78, one decimal, yeah, percent krypton, right? Times this 1060.529 moles. That I can do as well. Should be 827.213. We only have 2 sig figs there, but we'll just keep them for now. This is moles of krypton. 72. You are right. Okay. Stop yelling at me. I'll fix it. Alright, let me fix this. Okay. So, 763.581. Yeah. Great. Okay, so with that number, 763.58 moles of krypton, we remember from our handy-dandy periodic table from yesteryear, krypton is number 36. That has a molar mass of 83.8 grams per mole. And so, we end up getting, wow, quite a lot. 63,988 grams, which we will round to 2 sig figs, which should be 64,000 grams. Okay, so Cassidy, this 83.8, that's, I got that from the periodic table. So that's just the atomic mass of krypton. Which we will use to convert from moles. Okay, questions on krypton. Did you guys get that as your answer? Hopefully. Okay, good. Okay, and then so oxygen, we have that same number of moles. 1060.529 This time it's 28, right? Okay, great. Let me just... Is that just this part Elsa right here? Yeah, that would make sense. Okay, so 296.948. Looks like we have, was it 260? Yeah. Okay. And then we're going to take 296.948, multiply by 32 grams per mole. Remember that, sorry, I forgot moles here. Oxygen is 2 as a subscript, so you'll have to use 2 oxygens. And so what's that going to be, Elsa? It'll be more than 1,000, right? So what's it going to be? Oops. Yeah, I got that too. Okay. 0.336 grams with 2 sig figs rounds to 9,500 grams. Okay, so we had in this thingy 9,500 grams of oxygen and 64,000 grams of krypton. Okay, so that's quite a heavy tank because it's so massive, I guess. It's 420 liters. That's quite a bit. Quite a big thing. So, cool. Any questions on that one? What's wrong, Marissa? Did you lie to us? Oh, no. I don't know what you need such a tank for. Oh, okay. That's what it was. Look how mad Zoe got. She's just yelling at you. Wow. Yikes. She has road rage. I think that's what's happening. Yes, I'm sure. It's a convenient excuse, Zoe. Okay. I think this would be a good time for our break. You're driving in your living room, Zoe? That's not a good idea. We talked about this yesterday. When you're going to the kitchen, you can still park your car far away as long as you can, move the groceries by running or by taking multiple bags. You don't actually have to drive into your kitchen. So, okay, just so you know. Okay, cool. So, let's go ahead and take our break. Indeed, I know. So, let's see. Yeah, so come back about 4:40 or so, and we'll actually start chapter 6. Okay, so we're done with gases. See, not too bad. It's just math. We have completed all of our gas stuff. So, okay, I will see you guys in about